Good morning. In this session, I would like to demonstrate a detailed design of a shell and tube heat exchanger. In fact, you might have already observed that the model available within Aspen limited. Even if you try to perform the shortcut design option that is available under that model, you will be limited to calculating the heat transfer area given the overall heat transfer coefficient. I think all of you are aware that designing a heat exchanger is an iterative process. Unless and otherwise we know the overall heat transfer coefficient, we will not be able to calculate the area. Without knowing the area, we may not be able to finalize the dimensions so that we'll be able to calculate the overall heat transfer coefficient. So typically, we'll be starting with an assumed value for overall heat transfer coefficient, calculate the area, fix up the dimensions, and then recalculate the overall heat transfer coefficient using the necessary correlations. And if they match, fine. Otherwise, you need to go with another iteration. This is how the design is performed. But the model that is available within Aspen calculate only the heat transfer area given the heat transfer coefficient. You will not be in a position to identify the dimensions like shell diameter, tube length, baffles. Now, there is a separate module available within Aspen in order to do this kind of a detailed design in Aspen. So this is known as Aspen Exchanger. Demonstrate how to go about this design using Aspen Exchanger Design and Rating. So you can search for Aspen Exchanger Design and Rating. Automatically you will be able to see this. So click on this. Save you. So these are all the things that you will be able to do within Exchanger Design and Rating. You can design a shell and tube, plate fin, air-cooled exchanger, and so on. So I'll be selecting the shell and tube design. Create. So most often you will be able to see that the GUI, though there is a small difference between Aspen and this Exchanger Design and Rating, you can see the next, which is common. So you will be able to check up whether you need to provide any information on a given tab. Now let me press some of the default details. As I have already mentioned, I'll be giving the basic information that may be required, and probably we will review the design once we complete giving this basic information. We have two pure components. Cold fluid is freon. The flow rate is known to us, and it is being heated from 240 Kelvin to 300 Kelvin, and the pressure is 7 atmospheres. And the hot stream is ethylene glycol. It is getting cooled from 350 to 320, which is available at 2 atmospheres. Now we were given some pressure drop, so we'll try to provide this data into this Exchanger Design and Rating. Now let me press next. As you can see, unless and otherwise you address these red dots, you will not be able to identify the proper, you will not be able to complete the definition of the problem. So let me go ahead, say next. Now you can see some of these colored tabs need to be filled in order to complete the problem definition. But you can make some kind of a small analysis. Now in order to perform energy balance, out of the 4 temperatures, there are variables like inlet and outlet temperature for both the streams, cold and hot fluid. And there are 2 flow rates, flow rate of the cold fluid, flow rate of the hot fluid, and also you have heat exchanger. But all these variables are not going to be independent with each other. So you can identify what is the minimum number of variables that you need to specify in order to complete this problem definition. I'll change the unit system to metric. So we don't know the flow rate of the hot side. So the cold side fluid is entering at the rate of 10,560. This is kg per hour. And the inlet pressure for the hot stream is 2 atmospheres, which is given in the problem statement. And the outlet pressure is, the inlet pressure of the cold side is 7 atmospheres. Now by default, you can see the outlet pressure is written as 1.818 and so on. This is because there is a default pressure drop, allowable pressure drop on hot side as well as cold side. But in our problem statement, we were given with this default pressure in atmospheres as 0.67 on both sides. So the moment I put these values, you can see that the outlet pressure is automatically adjusted. Right? Now, we know the temperatures of all the four temperatures. The hot side is entering at a temperature of 350 Kelvin and the cold side is entering at a temperature of 240 Kelvin and the hot side outlet temperature is 320 and the cold side outlet temperature is 300. Just observe the moment I enter this information, you can see that all the required information will be enough. Automatically they will be turned into white because we have provided all the necessary data. The moment we know 4 temperatures and 1 flow rate, we should be in a position to calculate the second flow rate by energy balance. Right? Of course, though I did not mention the fouling resistance for this problem, you can take any problem involving fouling resistance. So if you define these values, the design will also be able to take into account the given fouling resistance. Now, most of the red ones are automatically addressed by defining this problem definition. But still, there is some more. You can expand this and try to see what are the other things that we need to define, right? So otherwise, you can go to next. Now it is asking for hot stream properties. Before we address these hot stream properties, we have to define the components that we are trying to handle. Probably in Aspen, this was the first step, but here it is coming slightly later. Now, you can select from any one of these packages, property packages, any one of them. For example, there are specific packages available for representing the properties of heat transfer fluids like CAM, Thermo, BJAC and so on. But in this problem, let me use only Aspen properties. Now let us define both the components that we are trying. Components only, ethylene glycol. So add use selected component. So this was added and we need to add another component which is freon or dichloro. This problem may be quite simplified in the sense, typically in any process industry, we may not be using pure components as streams. In fact, if your stream is a mixture of several components, define all the components and define its composition. Remember, we are talking about the hot stream composition, which is pure ethylene glycol. So I am defining it as 100% ethylene glycol. The weight flow rate is 1. Now we have defined this. So similarly, go to the next. Now we need to talk about the cold stream compositions. Again, we are using Aspen properties. Already the components are defined and the cold stream is now pure freon. So now you can see all the required input. There are no more red dots available. So all the required input for designing this problem is complete. So we should be able to run the problem. So I'm pressing next. So you can see all the required input is complete. So you need to, you can run the problem. We got to some results. Now you can check up these results in a systematic way. These are some warnings and they may not really matter, but if you want, you can deal with them. I'm clicking on optimization part. As you can see, the simulator was able to perform 4 different designs. You can identify the difference between these 4 designs. There may be some change in shell size or shell diameter, and the tube length, maybe the number of tubes. So there are variations. But you can see the number of what type of heat exchanger, number of tube passes. One in 2 cases, 1-2 heat exchanger in 2 cases, right? The number of shell passes are 1. Now, it was also able to estimate the cost of these exchangers, 4 different designs, and suggest the minimum cost exchanger as the final design. This is what is meant by optimization, right? So $12,755 has been computed. Now you can also look at the recap of designs. So whatever is the exchanger that is costing the minimum is automatically selected as the final design. Okay, and you can see all the results of your design in a particular format known as TAMA sheet, Tubular Exchangers Manufacturers Association. So whatever details that you want as far as this particular exchanger is concerned is available in a particular form. Similarly, there is another format, overall summary. You can also probably get all the design details in this particular format. Now, I am particularly interested in showing some details. Now, I'll go to the setting plan and tube sheet layout. I did not observe what is the number of baffles and so on. Can you see somewhere? You can probably check it up. So, depending on the number of baffles that were calculated in your design, this setting plan is drawn as per that scale, right? And you can also see the tube sheet layout. Now, this is, I think, 1-1 exchanger. So, we have a total number of, I think, 47 tubes, and we are arranging them in a triangular pitch. We never mention some of these details while specifying the definition of our problem. So the simulator must have taken some default values. If you are not happy with any one of these default values, you can go back, maybe change as per your requirement and redesign the problem. Now you can see the tubes, 47 tubes are arranged as per triangular pitch within the shell diameter that was calculated. The shell diameter was 205 mm, right? Now remember, whatever changes that you are trying to perform, automatically these drawings can be developed by the simulator itself. So together with the design data, along with these drawings, if you are able to send it to a fabricator, you should be in a position to get your equipment fabricated as per your design calculations. Now you can also see cost and weights. So the cost of the total exchanger is about 668 kgs, but when it is filled with water is about 826. And the cost of the exchanger is given as 12,755. Now you can probably see some other details. Of course, you can spend some time and try to see what are the various other calculations the simulator was able to perform. So if you try to see now, unlike the case of the model that is available within Aspen, we were trying to provide a constant value for the overall heat transfer coefficient. But here, you will be actually calculating the overall heat transfer coefficient on the shell side, heat transfer coefficient on the shell side and also on the tube side, and the corresponding numbers on both sides. So you can also see what is the MTD, LMTD, flux, duty distribution, and so on. Just go through these data. Pressure drop, we have given maximum allowed is 0.69. Of course, we set it in atmospheres, 0.67. Maybe in terms of kg force per centimeter square, it is this value. And these are the actual pressure drops that we had, right? Flow analysis. So please go through some of these details. Okay. Let me show you this. Now, typically when we are trying to design a heat exchanger manually, what we will be doing with respect to the properties, probably based on the inlet and outlet temperatures, we take an average and try to estimate all the properties at this average temperature and use these properties for the design. But what Aspen or what this simulator can do is, the given temperature range is divided into, by default, 11 zones. Of course, if you are interested, you can either increase or decrease this number. You are free to do that. So the temperature difference of 30, when it is divided into 11 zones, each zone corresponds to about 3 degrees. So it calculates within this 3 degrees what are the various properties. So at 76.85, what is the density, specific heat, viscosity, so on and so forth, which are needed for doing the design. Similarly, next 3 degrees, what are the properties? Until you come to the last zone. So you can see the variation 1072 to 1100 in terms of density, and especially if you look at the viscosity 3.3 to about 7.5. This kind of variation, calculating these properties in such small zones may not be possible when you try to do it manually. That could be one issue. And in the same way, you can also look at the cold stream properties. By default, it was dividing it into 19 zones. The temperatures are slightly larger. The difference in temperature is larger than the difference in temperature for the hot fluid. This is 60, whereas for the hot fluid it is 30. But anyway, once again, you are at liberty to change this number. Once again, you can see the properties are calculated within each zone. And in fact, the simulator will be estimating the actual amount of heat transfer taking place between the hot fluid and cold fluid in the zonal basis. I'm not sure whether you have been exposed to designing a heat exchanger using zonal calculations or not, but such calculations are not possible to do manually. You need to use some kind of a computer package. Now, the designs made by such commercial software, HXNet or whatever model that you are seeing in this, and you also have some other commercial software, they are enjoying quite a lot of reputation. The designs made by these software are accepted even by industry standards, right? Now let me go back to some of the details which we ignored in the beginning. We never said what type of exchanger that we are trying to design. In fact, it is available right in the first tab. Now what do you mean by the head type, shell type, rear head type? We never mentioned. By default, the simulator was using some kind of values. So this is the front head type. They are given B, C, N, D and so on. Similarly, you can see the different types of shell passes that are available. E, H, J, K, X, so on. Similarly, rear head type. So if you are interested in designing a particular type of exchanger, you need to select accordingly. And similarly, of course, you can also go into the other details. Let me go into the tubes. We never talked about the type of pitch that we are using, but you have a choice of varying them. Right? Whatever pitch you want, you can do that. I'll come back to this. Baffles. Now, by default, the simulator was taking a single segmental baffle, so you have other possibilities. Right? Similarly, you can also say what is the baffle cut. Right? So generally, 25% is taken by default. If you want the other way, you can also define this. Let me try to redesign this problem with some simple modification. Instead of triangular pitch, let me go for square pitch. You remember earlier we had 1-1 exchanger involving 47 tubes when we were using triangular pitch. What will happen if I switch on to maybe square pitch? Probably we can go into setting plan. Now can you see that they are arranged in square pitch? And what is the total number of tubes? Now the number of tubes increased to 64, and I think the number of passes on the tube side also are made too, right? Before this, let me also show you what is the optimization part, recap of designs. This was the design that we did earlier, which is costing something like $12,755. Now with this change, now the cost got increased to $14,474. As I said, this is quite capable. You can go into each of these details, and depending on your requirement, you should be in a position to deal with an appropriate design. Start with probably the default values taken by the simulator, and depending on your requirement, one by one, try to change and see what is its effect on the cost and also on the design. And you will be, as I said, you will be in a position to develop the required drawings present all the design data in the form of a particular template, which can be passed on to maybe a fabricator, get this equipment fabricated and installed. Let me address a few problems associated with this design before closing this particular session. Now you can see the heat exchangers typically you will be having number of components. Just go through. I think some of you are already aware of what are the various parts in a heat exchanger. Typically, shell and tube heat exchanger. So this is a typical 1-2 exchanger. On the shell side, there is only one pass. Shell side is entering here and getting exited from this. Whereas on the tube side, it is going through this part because there is a divider here. This is a 1-2 exchanger. So this is how the baffles will be able to create turbulence, which helps in increasing the the coefficient, heat transfer coefficient. But this might result in more pressure drop on the shell side. More number of baffles, more pressure drop. Similarly, you can also see different types of baffles that are possible. So I think what is the purpose of using a particular baffle? To create turbulence, increase the heat transfer coefficient on the shell side. Not only that, it may also act as a support in case of long tubes. So these are the other types of baffles. Now this is a typical bundle of tubes in a commercial heat exchanger. And these are the various types of front ends, shell types and rear heads. So they are typically given some codes A, B, C, N, D, and shell types E, F, G, H, J, K, X, and similarly rear heads. Remember all possible combinations of front end, shell types, rear head. For example, A, G, P. We don't know whether they are compatible or not. So you need to clearly check whether you will be in a position to use a particular type of front end with a particular type of shell. Similarly, what type of rear end it is compatible with. So all possible combinations may not be really possible. So if you try to look at the typical heat exchangers that are used in chemical process industry, AES. A stands for the front head, E stands for the shell, S stands for the rear head. Similarly, BEM. This is one of the most commonly used heat exchanger. AEP, floating head type BES, BEU, CFU, and so on. And if you try to look at some criteria, which you might have already undergone, some basic criteria, you will be normally putting a fluid on the tube side in case if you are handling a corrosive fluid, and if it is a cooling water, and if it is going to cause water fouling between the two, whichever is causing more fouling, you try to put it on the tube side. Less viscous fluid, put it on the tube side. Higher pressure, you put it on the tube side. And typically, in general, we will put the hot fluid on the tube side. And normally, when you are having a condensing vapor on the shell side, fluid with large temperature change also is generally put up on the shell side. Now, with this background, in fact, I did not go into many other components involved in this particular package, but you should be in a position to go through them, having designed a particular heat exchanger. So with this, I would like to stop this session.